Governance is often discussed in words: policy, legitimacy, power, risk, accountability, public value, institutional failure. But words alone can sometimes hide the structure of a problem. They can make sequence unclear. They can make constraints vague. They can make responsibility diffuse. They can make action appear justified before it's actually become admissible. This is why P develops governance mathematics, not mathematics as decoration, not formulas to make philosophy look technical, and not a claim that public life can be reduced to numbers. P uses mathematical formulation for a more disciplined purpose, to make the architecture of governance visible. Why formulae matter. A formula can show relations that prose may leave unstable. It can show that one thing depends on another. It can show that action should not occur before classification. It can show that signals must pass through constraint. It can show when overload, drift, or breakdown has begun. For P, mathematical governance begins with a simple insight. Governance is not merely decision-making. Governance is a structured process through which signals are interpreted, constrained, classified, tested, and only then converted into action, the core governance sequence. That is why one of P's central formulations expresses governance as a sequence: signal, constraint, ontology, admissibility, action. A system receives signals. It identifies the constraints that bind the situation. It classifies what kind of issue it is facing. It tests what forms of action are admissible, and only then should it act. When this sequence is bypassed, governance failure begins. Governance over humans and machines. Mathematics also matters because governance is no longer exercise only over human institution. Governance now operates across human systems and machine systems. It must govern people, organizations, markets, platforms, algorithms, automated decision systems, AI agents, sensor networks, financial models, digital infrastructures, and computational environments. In an increasingly technology-enframed world, governance must negotiate terrain that is partly social, partly institutional, partly technical, and partly computational. This means governance needs computational capacity. Governance must be able to understand systems that operate at machine speed. It must be able to evaluate models that classify, predict, optimize, and act. It must be able to detect when automation has bypassed human judgment. It must be able to test whether AI outputs have become admissible for institutional use. It must be able to distinguish performance from justification. Mathematics enables governance to operate across this human-machine terrain. Governance of formal governance. Mathematics gives governance a language for thresholds, mappings, probabilities, feedback loops, error costs, signal velocity, classification, and systemic instability. Without this formal capacity, governance risks becoming slower than the systems it is supposed to govern. It reacts after the fact. It regulates surfaces. It misunderstands machine-generated signals. It treats technical outputs as neutral. It confuses computation with knowledge. P's position is different. In a technomatical age, governance must be able to govern both man and machine. It must preserve human meaning, legitimacy, dignity, and public value, but it must also possess a mathematical and computational structure to understand the systems now shaping institutional life. This is why PII Governance Mathematics is not optional decoration. It is part of the future operating capacity of governance itself. Sequence formulas. PII Governance Mathematics includes several kinds of formulations. First, sequence formulas. These express the order
in which governance must proceed. Action should be a function of admissibility. Admissibility should depend on ontology, constraint, and signal integrity. Classification should depend on the constraints that apply, and constraints should depend on signals that have been properly interpreted. This allows P to show why premature action is defective. Speed is not admissibility. A government may act quickly. An institution may respond visibly. A market may move immediately. A media system may demand a conclusion, but speed is not admissibility. Second, P produces threshold formulas. These help identify when a governance system is approaching overload. For example, the Rucker-Virlio equation expresses a basic condition of modern governance failure. When signal velocity exceeds processing capacity, institutions become reactive. Thresholds and overload that matters in AI, media war, finance, public health, markets, and political crisis. A system may receive more information than it can interpret. It may react before it understands. It may confuse visibility with truth. It may treat urgency as justification. Threshold formulas help name the point at which complexity becomes governance risk. Breakdown and instability formulas. Third, PI develops breakdown and instability formulas. These describe conditions such as interpretive breakdown, post-semiotic drift, legitimacy, decoupling, correction shock, containment failure, and institutional overload. They help ask, when does communication stop producing shared meaning? When does legitimacy become signaling rather than constraint? When does containment become a substitute for repair? When does efficiency stop being governance? When does an institution continue operating while its meaning architecture has already failed? Technical and philosophical questions. These are not merely technical questions. They are philosophical, institutional, and public questions. But mathematical formulation helps make the relationships visible, repeatable, and testable. Fourth, PI develops set, mapping, and classification models. This is important because governance always classifies. It decides what belongs inside a problem, who counts as affected, which constraints apply, which risks are relevant, which category the issue falls into, which actions are permitted, which constraints apply, which risks are relevant, which category the issue falls into, which actions are permitted. Misclassification. Governance failure often begins when the wrong classification is made. A housing issue may be treated as a supply issue only. A public health issue may be treated as a communications issue only. An AI issue may be treated as innovation only. A legitimacy crisis may be treated as public relations. A financial issue may be treated as accounting while its public value structure disappears. Mathematics cannot solve these problems by itself, but formal structure can show when the wrong transformation has occurred. What formal structure reveals? Formal structure can show when an issue has been forced into the wrong category. It can show when a partially ordered problem has been wrongly flattened into a single ranking. It can show when public value has been reduced to cost. It can show when optimization has replaced justification. PI governance mathematics therefore serves several purposes. It clarifies sequence. It exposes misclassification. It identifies thresholds. It shows dependency. It distinguishes performance from justification. Operational structure. PI governance mathematics helps reveal when governance has acted too early, too narrowly, or through the wrong ontology. It gives philosophical concepts operational structure. This is why PI's mathematical work is not separate from its philosophical work. The two belong together. Philosophy asks, what is the issue? What is legitimate? What counts as harm? What is public value? What kind of action can be justified?
and philosophy and mathematics together. Mathematics asks, what is the structure? What depends on what? Where's the threshold? What sequence has been broken? What relation has been distorted? What transformation has failed? Philosophy without structure can become general mathematics without philosophy can become blind optimization. PI brings them together through admissible governance, or from memories and Bertmans, artificial intelligence, and automated systems. This matters especially in an age of artificial intelligence and automated systems. Machines operate through models, thresholds, probabilities, classifications, optimization functions, training data, feedback loops, and decision rules. If governance cannot understand these structures, it cannot govern them adequately. But if governance merely imitates machine logic, it loses its human purpose. So the task is not to surrender governance to computation. Formally capable, humanly anchored, the task is to make governance formally capable enough to understand computational systems while remaining anchored in human meaning, legitimacy, ethics, and public value. In a world increasingly shaped by machines, governance must not become less formal than the systems it seeks to govern. At the same time, governance must remain more than computation. It must ask whether action is justified, whether dignity is preserved, whether public value is protected, whether legitimacy remains real, whether affected persons are still recognized, whether the system can still correct itself. Machine-mediated reality, PI governance mathematics, exists at this intersection. It helps governance remain humanly meaningful while becoming formally capable enough to govern machine-mediated reality. PI's governance mathematics is ongoing. The goal is not to produce a closed system. The goal is to accompany PI's philosophical works with formal expressions where those expressions genuinely clarify the theory. Some concepts require prose, some require diagrams, some require doctrine, some require case analysis, and some benefit from formulas. PI disciplines ethics. It helps show when action has barred past the ethical and institutional thresholds that should constrain it. Closing. PI develops governance mathematics because modern institutions face problems of signal overload, legitimacy drift, misclassification, acceleration, technological opacity, and public value failure. In such a world, governance needs more than opinion. It needs architecture, it needs sequence, it needs constraint, it needs computational capacity, it needs admissibility. PI a discipline, not a trend. A framework, not an opinion. Frameworks turn complexity into admissible decisions.